Okay, in the second part of this lecture, we are going to talk about the geometrical nonlinearities. So this, for the rest of this lecture, as well as the lecture for next week, we will focus on geometrical nonlinear finite element method, and we're going to present one of the theories behind this geometrical nonlinear FEM. And basically, this theory has been well implemented in most of the finite element packages, and in Abacus, it all boils down into a simple option where you need to turn on for performing geometrical nonlinear analysis. However, it's my duty to go through this content with you at least once so that you have a feeling of the effort behind implementing that simple option. And I will start with the description of kinematics and the assumption of geometrical nonlinear deformation. Previously, we've presented two cases under geometrical nonlinear deformation. Case 1 is large displacement, small strain. That's the case with beam bending. Case 2 is large displacement, large strain. That's the case with rubber and pulling. And in both cases, the critical aspect is that the deformed configuration does not equal to the initial configuration. All right, this is the key issue here. And in linear FEM, we never made the distinction between the deformed configuration and the initial configuration, while in geometrical nonlinear FEM, we can no longer do so. Today, the formulation that I'm going to present is capable of covering both cases. Now, we start with the concept of configurations. The reference configuration here drawn is a known configuration. So basically, we know everything about this configuration, this body at this particular state. It could be the initial configuration of the body, right, before any loading applied. Then it's a fixed one. It could also be the last converged configuration, which we have already solved for. Under certain loading, if we either apply loading from the initial configuration or apply loading increments from the last converged configuration, this body would deform. It will deform to the so-called current configuration, which is unknown to us. This is a configuration that we still need to solve through iterations or through arc-length method, for instance. And I have a material point at location capital X. Under deformation, it moves to rotation small x, okay? And this is the map between the two. So I'm abusing the symbol a little bit. So small x is both the current location of the material point as well as the map that maps the same point between the two different configurations. And we consider fixed coordinate system, which means that the observer who was standing here in the initial or reference configuration is still standing here in the current configuration. We have a one-to-one continuous invertible map between configurations. This means that every material point will be mapped to a unique material point in the current configuration. And this mapping is continuous in time, which means that at arbitrary time, I can take a snapshot and I can observe the particular state of this body at that particular moment. It's continuous through the domain as well, which means that at the moment, I do not consider any crack in the domain. And it's invertible, which means that I can always go back to the initial reference configuration. This is so-called Lagrangian description, which means that the coordinates and the displacement, they are a function of the coordinates of the reference configuration, okay? So the current coordinate of the material point is a function of the reference coordinate and the time. Similarly, because we are using a fixed coordinate system, we can simply calculate the displacement as the small x minus capital X. And this displacement function is also a function of the capital X, which is the coordinate of the material point in the reference configuration, and also a function of time. And we can write these quantities in indicial notation, and note that because we have a fixed coordinate system, these unit vectors are the same. And under this Lagrangian formulation, we have two different types of Lagrangian formulations. The first one is called total Lagrangian formulation. That is when, as I mentioned earlier, the reference configuration is the initial configuration of the body, which is fixed. Now, if I talk about updated Lagrange formulation is very simple, which basically means that I update the reference configuration to be the previously converged configuration, which means the state of the body at the end of the previous increment. In practice, the two are very similar. All you need to do is to update your reference configuration at the end of your converged increment, but for illustration purpose, I will focus on the total Lagrangian formulation. So in the rest of this presentation, the reference configuration will be the initial configuration. Under kinematics, after we've introduced configurations, I would like to talk about deformation grading. This is a concept which relates a differential line segment, which is a vector here, to itself in the current deformed configuration. So d capital X is a small line segment in the initial configuration, and d small x lowercase x is the same line segment but in the current configuration. Okay, you can visualize here as well. How do we mathematically relate the two? The mathematical tool to relate these two quantities is gradient. So we can define a gradient matrix which is of such an expression because x, small x, is the u, the displacement vector, plus capital X, our coordinate vector. We can write this partial small x over partial capital X as the identity matrix plus the partial of our displacement vector over partial of our material coordinates or capital X. This is the definition of gradient. And with this gradient defined, we can simply write dx, d small x, which is the line segment in the current configuration, as the product of the F matrix, which is the deformation gradient, times d capital X, which is the vector, the same vector in the initial configuration. Of course, we can invert this deformation gradient to relate the d capital X, which is the line segment in the initial configuration, to itself in the current configuration. Now we can write this matrix Fij as partial small xi over partial capital Xj. I hope this is clear. After defined deformation gradient, so we have a relationship between material points through this mapping. We have the relationship between line segments through deformation gradient across the two different configurations. Next, I would like to talk about stretch and strain. So when we talk about strain, we talk about the change in length. We want to get rid of the vector, which is d capital X, but only extract its change in length. So how do we do that? Let's first define a concept called stretch. Stretch, which is usually represented by lambda, equals the current length divided by its original length. Right? How much we stretched a fiber, for instance. So if the current length of this line segment, d small x, is dl, and its original length in the initial configuration is dl0, then its stretch is basically the ratio over the two. Now, as I mentioned, that I would like to obtain the length of these vectors, d capital X and d small x, and the way to obtain length of a vector is to simply calculate the dot product between itself. Then we obtain the square of its length. Now we plug in the relationship between d small x and d capital X through the deformation gradient. We can obtain this expression for the square of the current length of this small segment. Then we define a unit vector of d capital X in the initial configuration. The unit vector is basically the same vector divided by its own length. Now we can simply divide dl square by dl0 square to obtain the square of the stretch, which we defined here. Now next, what I'm going to do is to plug in the expression of dl square, which is this one, into here. And I'm going to distribute dl0 square into the left and the right side of this expression. This means that I subdivide here by dl0, and similarly I do the same here. Then what I obtain is, on the left I have the transpose of my unit vector, on the right I have the unit vector itself. Alright, so I can simply write the lambda square as this expression. So after I have expression of lambda square with quantities like d capital X hat and deformation grading, I can define, based on stretch, the strain. And in our mechanics course year 1, the very basic strain that we define is simply lambda minus 1. Here is the change in length, which is dl minus dl0, divided by the original length, which is dl0. And you can write it in the form of stretch as stretch minus 1. Now we are going to plug in the expression of lambda here, and we need to take the square root, and you will obtain this expression. So this is the engineering strain that we are familiar with from undergraduate studies first year. But there is a problem. Okay, once we go beyond one-dimensional case, like a bar, and put it in a context of a three-dimensional space, we have this annoying square root appearing, and we can't sort out a nice matrix out of it. Okay, so unlike the Cauchy stress tensor, whereas you multiply the Cauchy stress tensor, which you can think of it as a matrix, by a normal vector, you obtain the stress on that surface. So here we cannot sort out a nice strain matrix, and this is something that is not undesirable. So theoreticians considered other definition of strains when we move in from a one-dimensional space to three-dimensional space. And there are some conditions that needs to be satisfied when we develop a new definition of strains. Number one is that the strain needs to be 0 when the stretch is 1, which means that when there is no stretch, you should not have any strain. Number two is that the strain must monotonically increase with lambda. So if there's more stretch, you have more strain. These are the two conditions. We can come up with a better definition of strain that can circumvent this square root operator. And this is called Green-Lagrange strain. In the Green-Lagrange strain, we directly use the expression of lambda square instead of lambda to form a new definition of strain. And in this new definition of strain, the strain is equal to 1 over 2 lambda square minus 1. Why this form? So, first of all, if we look at lambda and we take a limit of lambda being 1, we can see that this expression is very close to lambda minus 1. So you break this expression into lambda plus 1 times lambda minus 1. In the limit where lambda is close to 1, you have a 1 over 2 times lambda plus 1, which then gives you close to 1, and then times lambda minus 1, which is then your engineering strain. So in the limit of lambda equals to 1, which means that you have very small stretch, this is the same as engineering strain. And we plug in the expression of lambda square, and then we also express 1. We do a mathematical manipulation, and we express 1 as d capital X hat transpose times identity matrix times d capital X hat. D capital X hat is the unit vector. So when you have a unit vector transpose times identity matrix times the unit vector itself, you obtain just 1. And the reason why I do this trick is to sort out this nice matrix in the middle. This is our Green-Lagrange strain. So basically the nice thing about this strain is that now I do not have a square root operator, and then I can sort out this matrix which is independent of the unit vectors, and it pre and post multiply with a unit vector. I obtain the strain for the line segment along that direction. Okay, so this strain, if you observe it further, it's a valid strain measure, so it's equals to 0 when lambda equals to 1. It monotonically increases with lambda. It has no more square root operation, and it's symmetric. Okay, you can verify this symmetric. And the additional thing is that it operates on quantities that are defined in the initial configuration, which is the configuration that we know of. Let's take a closer look at the expression of this Green-Lagrange stress tensor. Here you can consider tensor as a matrix. And we plug in the expression of deformation gradient as the identity matrix times the displacement gradient. Then we obtain this form. So we can either write the Green-Lagrange strain tensor in terms of the deformation gradient or in terms of the displacement gradients. Now, I have talked about the Green-Lagrange strain tensor, and remember that in the linear finite element method, we use a different strain pair. We use this one. So it has a 1/2, then product of this one. This expression was the strain that we use in linear FEM, because it's a linear function of u. And this term is an additional term that we introduced in the Green-Lagrange strain tensor, which is a nonlinear function of u because we have the product of the two here. You have a square. Now, why do we need to use this one instead of just keeping using the linear strain tensor? Let me motivate you with a simple example. Let's consider this example where I have a square, first subject to uniform stretching along both directions. We have a stretch in one direction being λ1 and in two directions being λ2. Then subject to a rigid body rotation around the origin by theta. We can express the current coordinates of a material point, which is small x1, small x2, as a function of the initial coordinates of the material point, which is capital X1, capital X2. So we can express the relationship by this equation. You can see that this matrix represents the stretching, uniform stretching, and this matrix represents the rigid body rotation around the origin. So this, you can verify that this product of two matrix is our deformation gradient matrix. And the first matrix, I call it R, which is a rotation matrix. The second matrix, I call it U, which is a stretch matrix. This in continuum mechanics is called polar decomposition. So basically, we can perform this decomposition for every deformation gradient. So this is physically, it means that if you consider a line segment of small fiber, then it can deform through space either as by stretching or by rotation or by a combination of the two. And usually we can always think the deformation of that small fiber by as first stretching it and then rotate it. So rigid body translation will disappear when you calculate the gradient. So then we can calculate the displacement by simply minus the capital X from small x. Then we can obtain, you can do it yourself and verify, we can obtain these expressions for u. And we can calculate the Green-Lagrange strain matrix by using the first expression. So if you plug in F transpose, you have U transpose R transpose, then you multiply by F again, then you multiply by R and U. In the middle, you would have R transpose times R, which then equals to identity because R is the rotation matrix. So you are really here left with U transpose times U, and U is a symmetric diagonal matrix, so you immediately can verify that in the middle you should have λ1 square minus 1 and λ2 square minus 1. You left only with the diagonal terms. So off-diagonal terms will be 0. You can verify it yourself. Then you can plug in this expression of u into this expression for the linear strain tensor, and you will obtain the expression like this for the linear strain. So this is the strain that we used in linear FEM. Now, observe the two strains. On the top, you have a strain matrix that is independent of rigid body rotation. So theta, which is the angle of rotation, does not come into play. While on the bottom, it is a function of theta. Imagine that λ1 and λ2, they are both 1, which means that I don't have any stretch. I immediately go into rigid body rotation. Would you expect any strain on this body? No, right? It's just rigid body rotation. It should be 0 strain everywhere. So basically, if you have λ1 and λ2 equals to 1, then the Green-Lagrange strain would give you a 0 matrix, which physically makes sense. But the linear strain, what you see is that the off-diagonal terms would be 0, but the diagonal terms, because the cosine theta is not 1, you have a finite rotation here, the diagonal terms they do not disappear. So there are non-zero diagonal terms in the case of linear strain. So basically, if you were to use linear strain when you have a rigid body rotation, you would see artificial non-physical strains appearing. This is unwanted, and in a geometrical nonlinear case, you could have a very large rotation, so certainly we cannot use this linear strain. So that's the reason why we use green Lagrange strain instead of linear strain in geometrical nonlinear analysis.